In this lesson, we'll show you how a Monte Carlo simulation can be used to model the development of asset prices, such as stocks. The price of an equity share is something we've observed in the past. However, its future development is unknown, right? The only information we have is about past prices. Tomorrow, the company's shares could go up or down. Who knows? Let's look at the following formula. The price of a share today is equal to the price of the same share yesterday multiplied by e to the power of r, where r is the log return of the share. If this equation looks a little strange to you, remember the algebra principle according to which e to the power of a natural logarithm gives us the number we are taking a logarithm for. Here, r is equal to the natural logarithm of today's price divided by yesterday's price. So the two terms cancel out, and we obtain an equality. This is an equation we should feel confident with. Its main added value is it allows us to depict today's stock price as a function of yesterday's stock price and the daily return we'll have. We know yesterday's stock price, and that's fine. We don't know r, as it is a random variable. Brownian motion is a concept that would allow us to model such randomness. The formula we can use is made of two components. The first one is called drift, and the second one is the stock's volatility. A drift is the direction rates of return have been headed in the past. It is the best approximation about the future we have. First, we'll start by calculating the stock's periodic daily returns over the historical period. We only have to take a natural logarithm of the ratio between current and previous price. All right, once we've calculated daily returns in the historical period, we can easily calculate their average, standard deviation, and variance. We've learned how to do that, right? This would allow us to calculate the drift component, which is equal to the average daily return minus 0.5 times the variance. We recognize historical values are eroded in the future, hence a random component is included, 0.5 times the variance. The drift is the expected daily return of the stock. The second component of a Brownian motion is the random variable. It is given by a stock's historical volatility multiplied by z of a random number between 0 and 1. The random number from 0 to 1 is a percentage. If we assume expected future returns are distributed normally, z of the percentage between 0 to 1 would give us the number of standard deviations away from the mean. We can do that because statisticians have calculated the distance between the mean and events that have a given probability of occurring, a probability between 0 and 1. So, for example, the distance between the mean and events with a probability of less than 99.7% is 3 standard deviations. This is how we can determine the variable component of the Brownian motion. The equation of a stock's price today becomes yesterday's price multiplied by e to the power of the drift plus the random value. If we repeat this calculation 1,000 times, we'll be able to simulate the development of tomorrow's stock price and assess the likelihood it will follow a certain pattern. In addition, this is a great way to assess the upside and the downside of the investment, as we've obtained an upper and lower bound when performing the Monte Carlo simulation. These are the mechanics you need to understand when using Monte Carlo for asset pricing. In the next lesson, we'll apply this technique in Python.